Alright, hey, this is our last video of the unit, and we're going to tackle longitudinal waves. Just a quick review. We've already talked about transverse waves. I'll just draw a quick video up, just a quick little illustration here. Remember, transverse waves look like this, where the medium was, the medium was traveling this way, up and down. I'll put an M there, and the wave was traveling this way, and those were right angles to each other. Okay, compression waves are a little different. Compression waves have both of them moving in the same direction. I'm going to draw a diagram here, and then I'm going to pull a book in and kind of show you with a little illustration that's a little bit better than mine. But if you want a diagram that you can actually draw to refer back to, then maybe sketch what I'm going to show here. So a compression wave, a great example of it is sound. And sound is basically is air molecules in different locations pressed together in a real tight area. So here we go, kind of like this. And so what you see here are basically air molecules. And in every other location, the molecules here are pressed together really close, very close, you could say. And in other areas, like right here, the molecules are spread out. Now you might be wondering yourself, well, how does that work? How does that happen? Well, actually inside, I'm going to kind of focus out here. You can kind of see my hands here. Inside your throat, inside your voice box, you have two vocal cords. And those vocal cords, as air passes through them, they come together and they pull apart. And when they come together, they push the air together, which makes this high density area, which we call a compression. And then when they pull apart, they pull the air apart, which makes it what's like low density area, which is going to be called a rarefaction just a bit. And that on and off, on and off, on and off, on and off, on and off business is what gives you a sound wave, and they call that a compression. And so what's actually going on with the wave? Well, if you were to like look at one individual molecule, that molecule, all it would be doing would be going back and forth like this. It would just be oscillating back and forth, 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 back and forth. And so this would be the medium. I'll put an M there. And then the wave itself would be like moving to the right or to the left. And since these two are parallel to one another, that's what makes it a longitudinal wave. Let me bring in a textbook that has a pretty good illustration of this. And here it is. I'll kind of pull it out so you can kind of see it. Maybe try to focus a little bit. All right. So there it is here. And so you can see right here. Okay, this is where the compression is going to be. The molecules are fixed together. You can also do this on a slinky. So the slinky would be right here. This is going to be the compression. And what we call this is the rarefaction. All right. And when on the next investigation, if you want to, go ahead. To make a compression on a slinky, you just take the coils, pull them back a little bit, and just let them go. And you'll see that compression travel right through the wave. It's pretty easy to do. So that's a compression wave. All right. That's pretty straightforward. So let's go back to your to the guided notes and fill in the blanks real quick. So we have a longitudinal wave. This is a wave in which the motion of the medium is parallel, okay, to the direction of the motion of the wave. That's pretty easy. Longitudinal waves are also called compression waves. Let's see if I can focus that better. Whew, that's a little better. Examples of longitudinal waves include slinky waves. Okay, so slinky waves are compression waves. They can actually be transverse waves. It just depends on how you do it. Earthquakes. Okay, and that's pretty important with earthquakes. Actually, earthquakes can be compression waves, and they can be transverse waves. So either or, which is kind of interesting if you start to study earthquakes a little bit. And then the last part, or the last one here, is sound. Sound is a compression wave. It's not transverse. Okay, the molecules just move back and forth between me. The faster they move back and forth, okay, the faster they move back, the higher the sound like that. And the slower they move back and forth, the lower the sound like that. All right. All right. Compression. This is a portion of a longitudinal wave where the medium is pressed together. Okay, so if I go back up to my diagram up here, this would be a compression, compression, compression. Real simple. Alright? And then a rarefaction is a portion of the longitudinal wave where the medium is spread out. Alright? And then so this would be a rarefaction here and a rarefaction here. I'll do a slinky one real quick just so you can kind of see it. So if the coils are pushed together real tight and then spread out, and then real tight, and then spread out, and then real tight, and then spread out. This would be compression, 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 rarefaction, rarefaction, rarefaction. Wavelength on this would be every other rarefaction, like that. That would be a wavelength right there. Alright? Alright, the last little bit is a human ear. And instead of me trying to do an ugly diagram, I'm going to pull in a text and just kind of just briefly talk about how is it that the ear detects sound. And it's pretty simple. If you want to try to sketch this maybe in that open space there, that's fine. I also have a model of a human ear. It's on the cart. You can actually bring it to your desk and kind of look at it. It opens up and you can see kind of the pieces of the ear and how sound is actually propagated through the ear. But basically the sound waves come in. And then this guy right here, as it's labeled, is basically the eardrum. And basically what happens is that drum, like if this is a piece of paper here, that drum just oscillates back and forth just like this. So as those compressions come in, they press it and then come back and press it and come back and press it and come back. And as they do that, okay, then they move here's the hammer. They move the hammer, the anvil, and stirrup. Okay, and then that wave then progresses all the way through the ear. Okay, but the biggest part that I want you to know is that those compressions, as they come in, they make that eardrum move back and forth and back and forth and back and forth and back and forth, and that's how they produce sound in your ear. That's how the sound is transmitted in your ear. And if you got a really loud sound, remember this, we talked about this earlier. If you have a really loud sound, that means that amplitude is going to be really, really big. That means that's going to be a big amplitude. And what that does is that makes that eardrum vibrate a really big difference, has a really big vibration, and that could rupture the eardrum. That's what happens when you listen to really loud sounds like at a rock concert. The reason that's harmful is because it makes your eardrum vibrate, have larger vibrations than what it should normally have. And those large vibrations could rupture the eardrum, which thankfully it's not happened to me, but could be very, very painful. Alright, that's it. That's the last video, and good luck.